Okay, hello everyone. Uh, Today I want to give you an introduction to abstract algebra. Uh, this will be a course on different algebraic structures. This video will only be the first part. I started this series a while ago, and I got a lot of positive feedback from it. People thought that they could understand the topics a lot better than in their classes. They thought I was very good when it came to, explaining things in an intuitive fashion, which is so important in mathematics, in my opinion. But English is not my first language, and there were a lot of grammar mistakes. There were some audio hiccups here and there, and I just couldn't deal with it. And I said, let's give it another go, you know. So hopefully this will be a great experience for you, for students that want to understand algebra, not just, learn the definitions here and there, but actually gain real understanding on abstract algebra. So without further ado, let's get started. So the course will be divided in 3 sections. We'll study groups, rings, and modules. Each of these structures are incredibly important, especially in category theory, but in topology, in field extension theory, and other important branches of mathematics. But yeah, we'll cover groups, rings, and modules in this course, and we're going to get started with groups. Algebra can be a little bit abstract, and I understand that's a bit of the problem with it. That's why so many students have trouble with this subject. But it's important to understand that with any branch of mathematics, it's not enough to learn the definitions or even to do the problems, but also to ask yourself questions about the different topics you're learning. Try to gain real understanding of things. Without further ado, let's get started with groups. Okay, so what is a group? Well, a group is a set with a binary operation, and this operation, which we'll usually denote with a dot, and we'll sometimes call it a product. This will be the operation of the group. Well, it needs to be associative. There must be an identity, needs an identity, and every element is inversible. Now, the identity and inversibility, I think this is pretty obvious, but I want to put a little bit of emphasis on what it means for an operation to be associative. So this is very easy to understand. We'll say that the operation is associative if this diagram here if this diagram commutes, then the operation is associative. I think this should clear everything up. Okay, so what are some examples of groups? Well, the most important example are the integers under addition. This is a very intuitive and simple example, and the properties of this group specifically is so important that we'll dedicate a decent amount of the course just analyzing the integers under addition. Another, I think, very natural example is given X a topological space. The nth homology group, whether this is simplicial or singular or whatever, this is a group. Okay, there are more examples. I would say that these two are the most important one. I would say that the second one is slightly more complicated, but you'll need to learn both if you want to pass the course. Okay, now let's talk about subgroups. Okay, a subgroup. Oh look, this is kind of funny. My writing is going in this direction. Is this a group? I don't know. Maybe you should ask yourself that question as homework. I'm just kidding. It's not a group. What would be the operation here? That's absolute nonsense. Okay? You need to be careful. You need to analyze everything. Okay, subgroups. What is a subgroup? Well, this is easy. Okay, let's talk morphisms. Now, morphisms are arrows. Morphisms are the arrows. So groups are objects. These are the objects. And these are arrows. Okay, so you've probably seen these diagrams before in linear algebra. You should have seen a lot of this in linear algebra, like, commutative diagrams. So I'm not gonna go super in depth, but it's important to remember that phi is a morphism of groups if it preserves internal structure. Again, I think this should be pretty clear on what this is. Just in case, I'll review. This is the same as with linear transformations. What we want is that the morphism of the product is equal to the product of the morphisms of the image of the product must be the product of the images. Okay, maybe this isn't super clear. So one way you can think about it is, imagine A is a vector and B is another vector, and the operation is like a plus. Then this would be analogous to like linear transformations. Linear transformations are actually group morphisms. Not all group morphisms are linear transformations, but the inverse is true. So I would say this is more of an example. Okay, again, this is pretty elementary stuff. You probably learned about all of this stuff in linear algebra. Okay, but when we have arrows, the natural question is, when can we reverse those arrows? And that leads us into isomorphisms. Now, some authors have, in my opinion, an incorrect notation for isomorphism. The notation that I prefer is this. So phi, let's say that is a group morphism. Is an isomorphism if it's injective. Now, important, this doesn't mean that the arrow is reversible. We can't necessarily go back from G2 to G1. In order to have that, phi is a categorical isomorphism if it's an isomorphism that is onto. Okay, so an onto isomorphism, I also think it's very funny how my writing goes in this direction. I don't know, write in the comments, why does my writing go in this direction? I'm interested in knowing your answers. I want some of that engagement, if you know what I mean. Okay, so going back, G1 is then isomorphic to G2. Okay, Lie groups. I think we are in a position already to talk about Lie groups. What is a Lie group? It's a group with, wait, no, we can't do it. You don't know about, yeah, you haven't taken real analysis. Okay, oh damn it. I was really excited to talk about Lie groups. Okay, okay. Let's talk about actions. Yes, this is a really, really important topic. I would argue that actions are the things that make groups interesting. Okay? So what is an action? Well, you have a G that is acting, look at this notation here, onto a set. It acts onto a set. And you can think of this as a morphism between G and the symmetries of X. It's important, like, you know, you have G. Okay, so this is X, and G will like shuffle the elements of X. Yeah, it shuffles. You know, like, oh, you can't see me. I don't have the camera on, but I'm doing like this shuffling motion with my hands. So the elements are being shuffled, right? That's an action. An action is a shuffling of elements with respect to like a group. Okay, so a good example, I think the most intuitive one, is a group acting upon itself, and the operation is to just do the group operation. Okay, we have 5 minutes left. Okay, now let's talk about finite groups. So far, all the examples have given, you know, the integers and the homology groups of a space. Well, the homology groups of a space, they can be finite or infinite. Well, that depends on the space. They can even be trivial. Well, they exist. But I want to focus on finite groups. What is a finite group? Well, it's a group where every, like, G is finite, right? It's a group where the group is finite. Okay? Now, what are some properties that finite groups have? Well, if we have an element, then if we take the element to the order of the group, that will be equal to 1. So yeah, so isn't that crazy? You can take any group, any element, and you'll get the number 1. I got you. This isn't the number 1. This is the identity of the group. Remember that we use the number 1. I have explained it above. 1 is the notation for the identity element of the group. Okay. Examples of finite groups. The integers modulo n. These are finite groups. Those are like the only important ones. Well, we also have the dihedral group, which is like the symmetries of regular polyhedron. So for example, this would be, well, there is some debate because the order of the n is to n. So some people use like D6 to reflect the symmetries of the hexagon. Some people use D12, you know. So this would be D3 because we would have to multiply by 2. Yeah, this is D3, the symmetries of the hexagon. Okay, so I'm running out of time. I don't want to cover the entire thing. Okay, silo. Silo is analyzing the actions of a group onto its P subgroups. Yes, so we have this action here, and we are trying to find the number of classes. Oh, there is this theorem called Lagrange theorem that says that that the number of subgroups in a Oh, damn it. I forgot to define what a quotient group is. Okay, forget about this. We'll go back to it later. Okay, so what is a quotient group? A quotient group, it's a subgroup. Wait, no, this isn't what a quotient group is. A subgroup is normal if it's invariant by the action, you know. Okay. Yes, so that's a definition of what a normal, and we use this notation with this little triangle. If that's the case, we can define the quotient, which is to just, just take the conjugacy classes. Conjugation classes. Okay, that's it. That's all a quotient group is. You need to be normal so that this is well defined. But that's it. That's all that it is. It's a relatively simple concept. So with this, we can define silos by the silo theorems. They describe the actions, this action, the action that conjugates a P group. P groups aren't necessarily normal. So this P group isn't necessarily invariant, but they have very nice properties. You can check this. Check chapter 3. This is well described in chapter 3. And I think that's about it. I think we've covered all of group theory. There's more stuff, obviously. There's always more to learn. I could spend a couple of minutes explaining group representations, but I think we are overboard. Okay, so I want to end the video by solving a problem. The problem is this. Is there a group morphism between C and C plus C? Non-trivial. How many? Find all. Wait, find all. There we go. Okay, so we need to find all group morphisms that are non-trivial from C to C plus C. So because C is generated by a single element, which we have defined above, it's enough to know where we send A. And what we can notice is that for, sorry, not A, 1. 1 generates all of the integers. So it's enough to send 1 to any pair, and each of these defines a different morphism. So N would then go to NA and B. So these are all of the morphisms. Hopefully, I've helped you out here. I've given you a nice, intuitive way to understand group theory. Next week, we'll cover ring theory, and we'll probably going to get started on module theory, which is when, in my opinion, the subject starts to get really, really juicy. So you really don't want to miss that out. If you enjoyed the video, feel free to like and to comment. I really want to know your input. I'm always looking for ways to improve. Also be wary that, like, I'm a mathematician. I know this stuff. And if you're watching the video, you probably don't. So there's some stuff that you'll probably have to take my word on. So, in the last video, there was a lot. I got a lot of flack for not going into great detail on, what was it? On the symmetric and alternating groups. But that's not that important in group theory. Trust me, it's not something you should learn. Just skip over that part. And yeah, I also wanted to give an introduction to set theory in this video, but I thought it was going to be a little bit too much. And I prefer to, don't give less topics, but teach them well. Teach them in depth in a way that you can understand. So hopefully you've enjoyed it, and if so, please tell me. Okay, so I'm gonna stop now. Have a good one.